Understand. So Francesca, floor is yours. Thank you.
And thanks everyone for being here, even if it's right after lunch. And thanks to everyone who did this together. It's been very nice to have, it's always nice to go to an SMC workshop. So I'm very happy that I got the chance to be here and talk about this recent work, which is joined with Nicolas Chopin, who hopefully should arrive tomorrow, if I'm not wrong, and Anna Corba from Inside in Paris, which is where I was with 30 Kings. So we've been talking a lot about filtering in the morning, but this will actually be about using SMC as a sampling algorithm when you have a generic target phi, as I will introduce later on. And I guess that a lot of the time of the words in the title are not very familiar, and I will unpack all of that throughout the talk. As you can see, I don't have many slides, but I do talk a lot. So if you have questions, I'm very happy to be stopped at any point during the talk. I mean, the whole point of this is for people to sort of understand and interact. So if it's not clear, just stop me and I will do my best to clarify. So as I mentioned, the aim of this project was to look at sampling in general. So as in the sort of usual setup, we're interested in a probability distribution pi, which we might know only up to a normalizing constant. And when we are in this situation, there are two sort of things that we might want to do. The first one is to approximate integrals with respect to this probability distribution, where f, is sufficiently regular, but it doesn't need specification for the rest of the talk. One big motivation is Bayesian inference, but it's not the only one. In fact, I have to admit that most of the work I've been doing in the past has not been focusing on Bayesian inference, but on other problems in which you might want to estimate integrals with respect to a probability distribution. And the second one is estimate the normalizing constant. And the second aim is mostly needed when we want to do model selection or parameter inference, because in that case, the normalizing constant is what you can think about as being the marginal likelihood that you might use to do parameter inference, even in state space models, but not only in state space models. So now our aim will be to approximate pi. One sensible way to think about this problem is in terms of optimization. For example, we might want to find the distribution mu, which is closest to pi, in a certain sense, and I will be focusing on the Kullback-Leibler divergence, which is defined over here, mostly because this is a very nice divergence. It has been recently shown in a paper by Sebastian Reich and Andrew Stewart and some co-authors that is one of the few divergences for which you can do this without knowing the normalizing constant of pi. So there is a lot of interest in the Kullback-Leibler divergence in particular because of its nice properties. And I mean, there are a lot of algorithms that can be written in this framework. Possibly the most famous one is variational inference, in which you restrict the optimization problem to not the full space of probability measures, but some parametric family that you have control over. For example, multivariate normal distributions. Of course, normally you would like to do something a bit more sophisticated than that, but if you restrict your family and there is a parameter that you can optimize to get an approximation which is as close to pi as possible, then you can do things, and I would say that these normally fall under the spectrum of variational inference. Actually, if you want to solve this problem on the whole space and you put a certain geometry on that space, which I will make precise in the next slide, you can show that Langevin diffusions are doing exactly that. So when you implement an algorithm which is discretizing the Langevin diffusion in some way, then you are minimizing the Kullback-Leibler divergence. And this has been shown. I think the very paper in which they made this connection is a very famous paper by Giordanotti and Kinderhalter, which was a breakthrough mostly from the variational sort of functional analytic point of view, but it has had consequences in sampling as well. If you then choose a different geometry, you get a time variational gradient descent, which is closely related to this one. But again, I will make this precise in the next slide. This is a bit more recent and is also based on an SDE, like the Langevin diffusion, but it's a slightly different version of the SDE. More recently than that, people have been looking at tempering, which is a different way to perform sampling, which is not based on a Markov chain. And there has been a lot of interest in the connection between minimizing DKL and tempering. And so this work is looking at this particular objective, but is not the only one. Here I mentioned one, which is very recent and quite closely related, but it's not the only one. And I do apologize if I didn't cite others that you like more. So before moving on to some details about this, let me, talk about the two that are possibly more popular. So if you think about the Langevin diffusion, and you want to minimize the KL divergence, what you are implicitly doing is looking at a Wasserstein-2 geometry on the space of probability measures. So you embed your probability measures in a metric space in which the metric is given by the Wasserstein-2 distance. And if you do that, then you can derive a gradient with respect to Wasserstein-2 of the Kullback-Leibler that looks like that. And you can do gradient descent in that space. Now, gradient descent will not look like the one that we're used to in Euclidean spaces. It will look like a PDE. But if you look at that PDE long enough, you realize it's a Fokker-Planck equation, and so it leads to in a natural way to an SDE. And the SDE that you get out of there is a Langevin diffusion, and then you can use your favorite discretization method to get from the Langevin diffusion to an algorithm. That could be, Euler-Maruyama, and so you get the unadjusted Langevin algorithm. You can add a metropolis step, but any sort of algorithm based on the Langevin diffusion, you can see it as a numerical approximation to gradient descent in that geometry. If you use a different geometry, let's say Stein's geometry, in which the distance is, well, Stein's distance, which I didn't put over here because it's a bit ugly to sort of unpack. The gradient that you get is this one, which is very similar to the previous one, but now you have the presence of this kernel over here. And what you obtain is not one SDE per se, but a bunch of coupled SDEs. So these are capital N copies of the same SDE that are interacting through these terms over there. And you can sort of see that grad log pi is still there. There is no diffusion term in this SDE. So it's technically an ODE, not an SDE anymore, because the role of the diffusion is now fulfilled by the kernel itself. Now, these two bring very natural time discretizations because we have ODEs, SDEs, we discretize time, and we sort of know what to do with them. You take the time steps small enough, and you get something that you can implement and use under some conditions is close in an appropriate sense to the continuous time version of it. But let's look at tempering next. So tempering or annealing is, I will use the two words exchangeably, refers to this sequence of distributions. So you start from a mu0 that you can think of as your proposal, and then you want to target pi, which is your, the measure you're actually interested in. And normally you pick a sequence given by this geometric path so that the lambdas range from 0 to 1. And it's sort of intuitive to see that when you start at lambda equals 0, then you have mu0, which is easy to sample from. And then when you reach time 1, you are at pi, which is complicated, but as you move slowly, you will eventually get there. And this is the sequence of distribution that you use, but then a lot of different algorithms are based on this sequence. Here I'm mentioning some examples. Parallel tempering is one of them. SMC samplers is another one of them. Annealed importance sampling, which is really just an SMC sampler with no resampling, and thermodynamic integration. So when we started looking at this, there seemed to be some sort of divergence between the fact that Langevin-based algorithm have a justification that comes from optimization, but tempering to what we knew so far, or I knew so far, didn't seem to have the same connection with optimization. And in fact, it turned out while we were looking at this, that other people already checked this connection, and some of the results were already obtained, but from a different point of view. And I will try to explain what the two different points of view are as well. So to do that, I will need to introduce some optimization technique, which is not gradient descent. So what I talked about before was gradient descent. And if you think about Euclidean space, we know what we're doing. We have an ODE, which is following the direction given by the gradient. Let's say that we don't want to do that. We want to use mirror descent instead. So mirror descent is a sort of is already discretized per se. So it doesn't work in continuous time. It works in discrete time, because we move from one iteration to the next through this update. So now we have a functional, which in our case is DKL, but I'm phrasing this in a general setup because it will be useful to understand how we derive the connection with tempering. So we have a functional from the space of probability measures to R plus. And the way that we obtain these iterates is given by this recursion. So we start at mu0, and then we solve this minimization problem to get to mu1, and then we iterate until we reach a certain, stopping criteria. So this is made of two terms. The second term over here is a regularizer. This gamma is a sequence of step sizes. You can think about this in the same way in which you think about the time discretization step when you discretize an SDE. They fulfill exactly the same role. And what you have over there is a Bregman divergence, which is just a measure of distance between mu and mu_n. A Bregman divergence is a particular type of divergence, which can be written in this way, where phi is a positive and convex function. If you are in Euclidean space, for example, the Euclidean distance is a Bregman divergence. If you are in the space of probability measures, the KL is a Bregman divergence. So you just use divergences that can be written in this form, and you will see in the next slide why this is very useful. This part is a first order approximation of the functional at mu. So you basically Taylor expand where this is a derivative in an appropriate sense, and then you replace f of mu with this first order Taylor expansion. And the derivative that we use is the first variation, which I particularly like because it's defined in this very intuitive way. So we are not talking about gradients with respect to the Wasserstein-2 geometry or the Stein's geometry. We're talking about a derivative which is defined in the same way in which you define the derivative in R. So in fact, if you replace this space with just RD, all of this goes through. Because the quantities that are defined over there have the same definition both in Euclidean space or in the space of probabilities. And if you're familiar with that, this is a Gateau derivative in the functional analysis sense. So this is what happens for a general functional, and you can sort of see from there that it doesn't really look like tempering at all. So we need to choose our building blocks carefully so that we obtain something that matches tempering. So first, we derive, so this is the standard way in which you would solve mirror descent. You want to minimize this. A natural way to do that is to take the derivative and set it to 0. And this is what you obtain. So this part comes from differentiating the Bregman divergence, and this part comes from differentiating the part that is related to the functional, so the Taylor expansion of the functional. Now, you can sort of see that this is not particularly useful until phi has nice properties. Well, if you pick the Bregman divergence to be the Kullback-Leibler, then grad phi is just the log. And so you get this very nice multiplicative update, which is normally called entropic mirror descent. Entropic, because you use the KL, which is sometimes referred to as entropy. This already looks closer to tempering because we have a multiplicative update, but we have this part over here, which, you know, depending on the functional f, might lead to different results. But if you remember from my very first slide, what we care about is minimizing the KL. So our f is effectively the Kullback-Leibler divergence. Our objective functional f is the distance from pi, in which case that first variation that I described before is just this quantity. So is related to the gradients that we've seen before, because if you add a gradient over there, then you get the gradient of the KL in Wasserstein 2. If you then integrate with respect to a kernel, you get the gradient in Stein's geometry, but they are not the same object. So in a way, we're looking at a derivative in a different space, in particular in the geometry of mirror descent. And if you plug that in, then just because you have an exponential over there and a log over there, you get this recursion. So this is what the bottom line over here is entropic mirror descent for the Kullback-Leibler divergence. Now that looks a lot closer to tempering. Not exactly the same, but quite close. Yes.
So it just happens that this first variation, in this case, with this functional, it's equal to the gradient in the Wasserstein 2 geometry, or it would be true for other functionals?
It's not equal to the gradient in Wasserstein 2, because you need to add a gradient in front of the log to make it equal to the Wasserstein 2.
Okay.
But in general, yes. So the way in which you can think about the gradient in the Wasserstein 2 geometry is you obtain the first variation, which is this. And then because that's the derivative in the space of probability measures, and then you take the derivative in Euclidean space. That would work for other functionals as well. So now we've seen tempering a couple of slides ago. We have mirror descent on this slide. Can we put the one next to the other? And can we find a way to connect them? Well, the answer is yes, because if it wasn't, I wouldn't be giving this talk. So the pi appears both over here and over there. The main difference is we have mu0 over here and mu(n) over there. But if you just play with this recursively and you plug in the expression for mu(n), obtain using mu(n) - 1, and you go backward, then you obtain that these two are exactly the same if this relationship between lambda and gamma holds. And that's particularly nice because mirror descent, coming from an optimization point of view, they are particularly interested in giving rates of convergence for your iterative procedure. So for free, basically, you get that when you do tempering, you have this sort of convergence rate for the tempering iterate. So if you want to know how far your iterate is from pi, you need to start from the KL pi to mu0, and it's not a typo, they are actually swapped, because this one is your objective functional, and this one is the Bregman divergence that you use. So you swap the role of pi and mu0 in the Bregman divergence. And then you can write down your rate in terms of gammas or in terms of lambdas. So pretty much that gives you a way to control how close your n rate is to your target. And it doesn't really give you a strategy to select lambda and gamma, but it tells you if you decide to fix your sequence of gammas and of lambdas to a particular sequence, it tells you how many steps you need to do to get close enough. Now, clearly, the fact that you need to choose gamma and lambda is suboptimal. We would like a procedure to choose them on the fly without having to fix a sequence from the start. In the mirror descent literature, what you would normally do is just set gamma constant through iterations to a sufficiently small value. And then you get a rate, which is a bit more explicit than that one, and you count how many steps you need to be close enough to pi. But we know from the tempering literature, the SMC important sampling literature, that we have ways to do this adaptively. And so we want to sort of bring this knowledge to the optimization, side of things and check, well, is it optimal in some sense? Does it have some connections that we can use? Can we say that you should use that tempering, the adaptive tempering rules for mirror descent? And the very step to do that is to notice that this tempering recursion can be written as an exponential family with parameter lambda. This is not new. I just put it on the slide because it's useful to see what's coming next. So you have lambda is your parameter, then you have this, which I will call score, even if technically is not what is normally referred to as score in like the Langevin word. But once you write this as an exponential family, a lot of things come out very nicely. For example, if you want to compute the F divergence between two successive iterates, let's say lambda and lambda 1, you can approximate it by using the fact that this is a parametric family in this way. So the first term is just 0 because an F divergence is defined for every F which is sufficiently regular and the derivative at 1 is 0. So the first term drops because of that. Then you have this second term over here, the derivative at 1, which is just a constant, and this quantity over here, which is just the Fisher information in the sort of parametric model sense. Okay, this gives us a way to control the distance between two successive iterations. Why would we want to look at divergences in the first place? Well, mostly because the chi-square divergence is one of them. So is the KL, and the chi-square divergence is what is approximated when using the effective sample size in SMC. So this, in a way, is connecting what is normally done in the SMC important sampling literature to a different point of view, if you want. Now that we have this way to express the distance between successive iterates, what can we do with that? Well, one natural way is to ask that successive iterates are sufficiently close. So they should be sufficiently close, and hopefully we want this distance to be constant over iterations. This is just to guarantee that we don't move too far in one step. And so our then numerical algorithm will solve. So to guarantee that, you basically set this to 0. So if you're at lambda n and you want lambda n plus 1, you just set this to a constant, sorry, not 0, and you solve for lambda n plus 1. And that's what you obtain. This is an ODE. And for some particular models, you can solve it analytically. And this is something that we looked at, not because it's useful in practice, but because it's useful to understand. So these are 3 examples. These are all Gaussians, because those are the distributions that we can, for which we can derive everything analytically. The first one, so the solution to this ODE in that case is this one, and is basically when you want to move from mu0, which we always take to be a standard Gaussian, to a pi, which has the same mean, so mean 0, but variance which is more concentrated. So if you are in that case, you want to move from a diffuse distribution to a concentrated distribution, then the optimal lambda is this one. So you move fast at the beginning and then you move more slowly, and corresponds to a constant gamma rate. This is what, when you implement mirror descent, you will normally pick this regime, constant gamma. But the aim of this couple of plots is to show that constant gamma is not necessarily the best that you can do. Because what you want to do is move as fast as possible and as reliably as possible. So if you are in a different scenario, let's say that now your mu0 is still a standard Gaussian, but you want to move to a distribution which is more diffuse, then you don't need to take a constant gamma to move as fast as possible. You need to take a gamma that behaves like this blue line. So what you have over here is the corresponding lambda, and down there is the rate of convergence. So you can, it's reassuring that all rates go to 0. So if you do enough steps, you will converge to where you want to be. But to have the fastest convergence, you don't necessarily want the constant rate. And the last case over here is an even simpler one in which you start from a standard Gaussian, you want to move to a Gaussian which has the same variance but a different mean, which is given by M. And again, even in this very simple case, choosing a constant gamma is not the best idea. So this sort of motivates us to look for adaptive ways to choose gamma and not just fix your gamma and do what in the mirror descent literature you would normally do.
Francesca,
Yes.
do you have an intuition as to why if you're targeting something that's more diffuse than your initial distribution, you have to accelerate?
Yes, and is because when you asked me about more diffused.
Because
Then-
you said like you had to accelerate. right?
Yes. In a way, this is the opposite of that. So they are related by the fact that when you want to move from something which is quite concentrated to something that is more diffuse, at the beginning you can allow to just move around a bit more at random, if you pass me the term, like just diffuse as much as you can do bigger steps. And then you want to move more slowly to get where you want to be. And if you reverse the roles, then you want to do the opposite. So to show you in one simple setting why constant gamma is a bad idea, this is what you get out of an SMC sampler if you use the standard adaptive strategy that we are all familiar with, or with the fixed gamma, which clearly needs to be small enough for the distributions to sort of make sense from a computational point of view. So we start from a standard Gaussian, we move to something which has a different mean and a smaller variance. And if you do the adaptive version, you get, a cloud of particles that seems to be doing a pretty good job. In this case, you get a cloud of particles which is in the right place, but is unable to capture the mode. And also it takes a lot longer to obtain this plot than to obtain that plot. Which is why we like adaptive strategies. And in this case, in which you not only change the mean, but you also change the variance, then the ODE that you get is a sort of hybrid between the previous one. You would get an S-shaped behavior for gamma. So you would get something which is like that. So you move fast at the beginning and then you slow down and then you move fast again. Just because you have to diffuse and then concentrate and then re-diffuse. Okay, so what I've been talking about so far has nothing to do with algorithms per se. I only talked about a sequence of distributions. I haven't told you anything on how to make this practical. How do we implement this? I will talk about one particular algorithm, which is SMC samplers, because we're an SMC workshop. There are others that I will briefly mention. If you're interested, I'm very happy to talk about it more. So we focused on algorithms that can be written like that. So what we have with this sequence of distributions in mirror descent is that mu n plus 1 is given by mu n times this exponential update, where this gn should be the gradient of the functional. In practice, you don't have the gradient on the functional, so you will approximate it with some g. And you don't have mu n, you have some approximation of mu n. We will be looking at algorithms in which this part, the information regarding the gradient, is carried by the importance weights. And Qn is just a mixture. So in the case of SMC, is a mixture of Dirac masses. But there are other options in which is, for example, a kernel density estimator that would also fall into this framework. The only one, well, one of those that I can think of that doesn't really fall into this framework is parallel tempering, which uses the same sequence of distributions, but doesn't really have this structure. So we cannot really identify, importance weights, carry the gradient information, and then the mixture part carries the previous iterate information. If you look at SMC samplers, then your approximation of mu n is a weighted average of Dirac masses. Your weights, that can be written like that, carry the gradient information, and using the connection between lambda and gamma, we can actually write them in this form. So they really are telling you how far you have to move from mu n minus 1 to pi with this step size. And then, you know, there are other bits of the algorithm, like a resampling scheme and the mu n invariant Markov kernel, which is what allows us to write the weights like that. But they don't feed into the mirror descent part. These two ingredients feeding into the mirror descent part. So why should we look at SMC over other options? Well, first, because I like SMC, but also because it has been studied for a very long time and compared to some of the other options that I will briefly mention later. So there is a lot of theory for it. People have been using it a lot. So that actually everything that I described about F divergences and choosing the lambdas adaptively. And I said, oh, but we can only do it, for special distributions because we can solve the ODE. Well, if you use your ESS strategy and you set, the next lambda so that the ESS doesn't fall below a certain threshold, you're already doing that. Because the F divergence that you pick is the chi-square divergence. The ESS is connected to the chi-square divergence, and so implicitly you're already doing that. You're solving that ODE. With the advantage that this is easy and inexpensive to compute. Of course, you can think of different ways to approximate the chi-square. You can think of ways to approximate the KL, but it's reassuring to check that the ESS is actually, we're already doing something that is pretty clever, which is what I'm writing over there. So you need to sort of rearrange a bit the terms because the ESS is actually n, the chi-square divided by n, but it doesn't really matter that much. And this strategy in particular guarantees a scaling with the dimension, which is quite favorable. So if you are in a scenario in which your kernels are very, very good, so they don't need to scale with the dimension, they are already perfect, which is a lot to ask, but let's say that we are in the best possible setting. By choosing this adaptively, you get that your sequence of distribution scales as the square root of d. Now, this is not technically a proof. This is a plot that shows that, but we are working on the proof and we are quite convinced that it is the case. And then when you have kernels that are not exact kernels, don't mix perfectly, then the scaling of the dimension of the kernels will feed into this scaling as well, probably in the way that you would expect. So other options, annealed importance sampling is, well, the same as SMC, but without resampling. So a lot of what I said actually carries over. Particle mirror descent was proposed recently, targeting mirror descent. So at that point, people had not started looking at the connections with gradient, with mirror descent, between mirror descent and tempering. So they developed an algorithm that would approximate mirror descent. The weights are incredibly similar, but because they didn't sort of spot this connection, they actually approximate this with a kernel density estimator, which is over there. And so their weights are linear to compute. So overall, this algorithm is n squared. And also, you have a bit of additional error due to the fact they use a kernel density estimator, while the weighted average that you use in SMC does not introduce that. But besides those 2 points, particle mirror descent is effectively just SMC with some tweaks. The second option is more related to regularized adaptive importance sampling. So also in that case, they use these weights with a kernel density estimator over there. But now you don't have capital N particles that get resampled over time. You just add one particle at the time, so the small n, not capital N, and you use the past particles as sort of burn-in period. So this is less expensive computationally, but we couldn't really phrase it into an SMC point of view. So the analysis that they have in that paper is ad hoc for this particular algorithm. Am I running out of time? Okay.
Any questions?
Okay, so I mentioned briefly that we were not the only ones to look at this, and I also apologize because I probably haven't cited everyone that I should have, but two papers in particular looked at the connection of minimizing the KL tempering, but not a mirror descent. They look at gradient flows, so gradient descent effectively. Not using any of the distances that I mentioned before. So not Wasserstein 2, not Steins, but the Fischer-Rao geometry, which I put down over here. Fischer-Rao is what I think has become more popular recently, but effectively this is one of the Hellinger distances. So let's say that now you have the space of probability measures. You metrize it with this distance. You derive the gradient flow, which is, fancy way to say gradient descent in the space of probabilities. You obtain something that looks like that, which is a PDE. And then if you rearrange it, then you get this expression, which is exactly what we had for entropic mirror descent. Because if you discretize with Euler, then you have the log at mu n minus the log at mu n minus 1 equal to minus f prime of mu n minus 1. So effectively, mirror descent starts from a discretized in time sort of optimization routine. If you look at the gradient flow, you are in continuous time, but then you just apply a simple forward discretization and you obtain the same result. So the rates that they obtained in this work are quite similar. They are, I think, obtained under some sort of more restrictive assumptions because working in continuous time in that case is a bit troublesome, while the rates that I showed are obtained under virtually no assumptions. So we only need the KL between pi and mu 0 to be finite. Once you have that, you can obtain the convergence rate. That's only because we use discrete time already, so we don't have all the troubles of working in continuous time. But it's nice to know that, you sort of get to the same result from different views because it means that it's probably close to be correct. So in conclusion, what this talk and this paper is about is really just trying to justify tempering from an optimization point of view. We looked at mirror descent because it was easy to deal with and also because Anna has worked extensively on it. So she was very familiar with all the results. What brings to SMC, I think, is, some nice connections that we can use to maybe inform future algorithms. For example, changing the divergence. Does it lead to something that is better than tempering, that is worse, or something that we can even implement? I don't know. I hope so, but I cannot tell for now. And on the other hand, I think it provides numerical methods to the people that are mostly interested in mirror descent, which have been around for longer. And so they have nice theoretical properties. They have nice adaptive techniques. So in a way, I think it might be the case from my point of view that is more bringing into the mirror descent literature from the SMC one than the other way around. I know one more than the other, so I cannot say that for sure. And yeah, the adaptive strategy based on the ESS or any other approximation of the chi-square seems to be the right way to do it. And it might be very beneficial to use also in those other algorithms that I mentioned that come from the mirror descent literature. That's all. Thank you.
There's not a few questions.
Is there an SDE that corresponds to the Fischer-Rao geometry?